So now we will I mean the next project will be Pure Nar, Hamad, Vibion, Simon. I don't know if Vibion and Simon they are online.
No, I don't think they are online.
Okay, okay. So please, Pure Nar, try to share your screen.
Yeah. So we are looking into this automatic license plate recognition, and then we are.
Can we ask people first if they can hear you?
Can you hear me?
Yes.
Okay, very good. Thank you.
So we are looking into the automatic license plate recognition, and then using this steganographic adversarial attacks against deep learning on top of this. So to be able to fool the algorithms to misclassify. So the working principle is like the previous examples that we are first locating the position of the car in the image. We are then extracting the number plate from the car's image, dividing the character present in the license plate, and then classifying and recognizing each character.
So here you can see the how generating like adversarial examples. So there are like steganography is a kind of you add some secret information to an image, and there are different types of like adding the secret information into image. Like you can do it in the spatial domain. If you do it in the spatial domain, like it might be faster, but it like adds any information directly to the pixels. So, and the other way to do is transform the domain into the frequencies and add the coefficients of the secret information into the frequency, and then reverting that into the spatial domain. So in this way, it might be not so much visible to human eye, but it can be detected with the computers or the processor. And adversarial attacks can be the white box or black box, and the other one is like it can be targeted or untargeted. Targeted means, for example, if you have class X and you wanted to classify it as class Y, which is wrong, and then it would be the targeted adversarial attack. And if you want to misclassify class X into any class, like it can be A, B, C, then it is untargeted adversarial attack. And there we have mentioned some of the existing systems for generating adversarial attacks. The first one is like spot area attacks. What they do, if you see here in the image, in the B with the circle spots, they are like circle spots generated on the source image, and how they are doing is like they are identifying the location based on the genetic algorithm by doing the like crossovers and mutation, and they generate the circle spots on different locations, and then find the probability of like how much they are misclassifying the source image. And the second one is the probabilistic analysis of the targeted attacks using transform domain. And in this, they convert the they are using the MNIST dataset, and they are converting the MNIST image into the frequency domain, and then they have carefully decided the watermark, which is a kind of, we can say, secret information or noisy data into the original image, which is decided using the CNN model. They like it's an existing model which they are using, and if you see in these images, we have like 9 columns and 3 rows. The first row is the original image, and the last row is a kind of like generated image for adversarial example. So we are not like reinventing the wheel. We are using the existing techniques to like create adversarial examples to attack the deep learning based ALPRs. And we are doing the untargeted attack. That means, for example, if we are targeting a character A, so it is misclassified as 9 or 7 or 6. So we don't care about that. We are not targeting like it should be converted only 8 into 7 like that. So we call it as untargeted attack. And the second one is black box attack. Like we cannot know the internal parameters of any deep learning models, what type of parameters they are using. So we don't have the internal information. So this is a kind of black box attack for us. So here is the proposed framework. What we are doing is we take the original image and then we are using the existing technique of Yole to detect the car. And then after that, we have tried the WPODNet for detecting the license plate, but like speed of this algorithm is not pretty good. It's very low. So we are thinking about using the hard cascade classifier, which is very like simple machine learning based and very fast. So if we can like we will be able to detect the number plate using this technique, then we will go for the hard cascade classifier. So our target is like to attack the real-time systems on runtime instead of like just testing the examples on some models. And after that, like simple using OpenCV, we find the characters, and later on, we are using the mobile net, and this is also an existing model which we are using to recognize the characters. And later on, we randomly select any character which we want to like we want to convert into the frequency domain and add some noise into it using the steganography techniques. And after this, like if you see the transform, we are using this method, probabilistic analysis or target X. We are using the MNIST dataset to do it. And but that is like binary images, and like so our target is to transform the RGB into the frequency domain. So each channel is transformed into frequency and then adding the watermark into each each channel. And after adding the that noise into each channel, we will reconstruct the image, RGB image from those frequencies, red, green, blue, and then after combining that, we will regenerate the character again with some noisy data. And after this noisy data, we have like you can see stable steganographic image, and later on we will blend this character into the original image so that we can feed the whole image to the network, because we don't know at which step they are recognizing the character, or at which step they are like detecting the plate, or whether they are directly targeting the car or not. So we don't know about the internal parameters of any technique or the system, ALPR system. So we are taking it as a black box and giving it as whole image instead of only number plate or instead of only car. So we just stenographically blend the image into the original and then feed it to them.
But black box, it's more difficult than white box. So you are selecting the most difficult direction. But how do you generate the watermark?
This is being done in this technique, probabilistic analysis of target attacks. There is a CNN-based deep neural network, and so we will be using that technique to generate the watermark.
Okay, and this one is for black box models.
Yes. And we will see that how it is for the characters, as we are dealing for the characters. We call it black box because we are like feeding the original image after adding some noise into it. And this deep neural network, which I am talking about, is to generate the watermark. They are using it for the MNIST dataset. So we will include like more characters and test it with all the characters, and then generate the watermark based on that. After that watermark, we can like incorporate that into the.
Yeah, but we need also to test maybe it's enough for the digits, right? So maybe we'll need the characters, maybe it's enough to add some noise to the digits, and in this case we'll make it confused.
Yes.
But can you maybe in the future can you make one time and you just do it first for images in the sets and explains algorithms and so on. So can you do it first for the image, for example, and then give presentation
Yeah.
and describe math behind it and after that we will apply it for the images. But we need to understand it first for images.
Yeah.
It will be easy.
So we are not like reinventing the wheel. We are using the existing technique. We chose one ALPR system for license plate recognition, and then we use the technique, choose the technique for the adversarial attack, for which is being used for the MS data because we are dealing with the characters here and the digits. So we will be like using two different approaches to come up with a new application. So
But
this
in
is
the
our-
phase first, we need to build our system as normal. And the one that accuracy is 95% something, and we will be ready for it. So the second phase would be to generate those adversarial samples.
Yeah, for this, for making the normal system, we have already developed it until the character recognition and mobile number plate. Like,
But we have to make it go in runtime.
yeah. So
In real time.
Yeah, in real time.
currently it is not real time, so we want to make it real time. So that's why we will be trying to use some basic machine learning to detect the number plate instead of going for deep learning.
What about, for example, in the way this easy part, because we can part on the can, what can we use in the way those companies easy part which you don't know because I mean it's accurate all time. I don't know. Did you part one time and then you did it? Did you try to part without getting a very one time? No, which means that they have accuracy almost 100%. So what algorithms they use?
Because it also depends on what type of data you're doing. Where your camera is placed. If it is placed outside the parking, then it's like easy because the view is most probably clear.
That's correct.
And if it is placed on the roads or somewhere, then it might be little difficult to detect the place and all this.
I guess that angle and light conditions they are quite good when they are
Yes,
right.
correct.
Yes.
Correct.
So, and the location of the camera, so it is easily visible, and they can easily use simple OpenCV techniques to find the blobs and identify them instead of going for deep neural network.
Okay, but we're using OpenCV, it will be impossible to attend those users, right?
But for the recognition, They
For
have to-
recognition, they use the
and it is important. If not deep learning, they must be using some machine learning techniques. So actually, they will have some classifier to recognize the character. So we can prove that whether it is deep learning, and because we are not targeting the white box, as it is black box. So whether it is simple machine learning algorithm or deep learning classifier, whatever classifier we don't know about. So we are giving it original image with some kind of adversarial attempt so that it can misclassify digits and classify it as some other plate or something. So
I
this
mean,
is the-
you group and the first group, is there any chance to group together, for example, and trying to exchange? Because today they show us some results.
Sure, because they are focusing mostly on the first part, and we are not, because we are just trying to do something that is already existing and maybe focusing on the last part.
So I wish if the two groups can work together, it will be very important. So we can speed up and people can just work together, develop what they want. And we have also another group who will do the same but for face recognition.
And this decision of watermark for each digit, this will be a one-time process. We can generate the watermark for each digit in one time during the deep neural
For the
network.
whole data set.
Yeah, and then later on for targeting, we can use that for each.
But
digit.
untargeted, it's much easier. That is untargeted. When
Yeah.
it's targeted, it's more difficult.
Yeah, we have to just misclassify the we don't.
But if you can prepare one time, maybe 1 hour or something for English and explain the name, the content will be very good.
Yeah.
Because now we have some reference, some papers.
Yeah.
So if you can do it or using the code also, okay, this is algorithm, and this is how we implement it. Okay, this is the watermark, we add it to the image, and so on.
I guess we will be able to explain maybe too.
Okay. This is
This is where like after we generate a watermark,
Mhm.
and we can just save it and target the digit based on the digit, recognize digit what we are targeting. We can use that watermark as a device and do it. And our main target is to do it on the rail.
But in fact, to be practical for for license dates, you mentioned a method here called spot
Yeah.
invasion. This spot
For the-
invasion attack. This is exciting because usually if you have your car and you want to attack some algorithms, I just need to find a spot and stick it to my driving plates. I will not add because my license plates it's not an image, it's in my car. So we need to generate some graffiti or something and stick it to my. So we need to generate how will generate it, what will be the location, and I need to get a spot or something to stick into my license plates, so systems will not be able to recognize it. Right? So this is so, but we will go for this approach.
In that case, that would be kind of defending the adversarial input. But we are kind of generating the adversarial attack.
Yes, I know you are generating those adversarial attacks for digital image. But my car, for example, if I'm driving outside now, I want to park, so I want to find a solution, right? So I need to get this universal patch, stick it to my car, license plate, for this spot, right? What is the location? It will be exciting, but this one is they use genetic algorithms because I need to make some changes beforehand, changes which will give me high accuracy, right? Or lower the accuracy of the machine learning which detects. So because at the end we need to get this stick and this, we need to stick it to one driving license. Right? It's like those universal batches classes. So someone will be classified as someone else. Okay. Yes. So thank you very much, Ahmed, and Fiona for and also the rest of the team for this nice presentation. So, any questions to Ahmed and Fiona? Any question? Ahmed, any question? No.
Just I have the first question. Maybe I wasn't I couldn't hear very well, but what's the first part like for face recognition? Which one have you? You said that you haven't. You don't want to focus on the first part of the project because it's already made.
Yeah, we actually at first when I did this assignment one, I just found a tutorial online which also Ibrahim published on Blackboard. So and that one is it's using YOLO to recognize the car, and then it's using WinCoordNet to detect the car plates. So we're planning just for now at least to continue using that one and then focusing on the last part, and also to have it in real time.
Because at the end we need to build a venue and we need to build some license plates for example and test the system.
Yeah, I'm just asking because there are different groups that are using different models. Like there is one which that has already been built. This is YOLO. I don't know it is based on which algorithm.
But all I mean we have two teams now working in this project and all of them they are using the transfer learning.
Yeah.
So the first team they use the BGG system. And in the Nicolau, he was presenting this ResNet scheme, for example, the team said it's more accurate, and he is proposing it to Leo and Mohammed to use it. And in your case, we're using this W.
Yeah.
It's also it's a transfer learning, so it's a for generating this minimum volume.
Yes.
It is using YOLO, so it like it's a kind
What is YOLO?
You only look on it. You only look on it. Which is used for the object detection and recognition. It is very fast. It works on maybe 240 FPS.
It's used a lot in real time.
Yeah. So we are targeting this one. So our main target is to attack on real time.
If you can also share codes from who's using this YOLO. With me, for example, it will be nice because we can edit to GitHub, for example, or we can make a problem for Yeah, because this is a good example, it would be very inspiring for us. So if we can just have this one with a data set, for example, and so people can just see what it's.
And for we are using Yoga because we want to like reduce the computation time as much as possible in the search area. If we have the card, then our algorithm for detecting the number plate does not have to search whole image. It has to search only extracted part of the card.
Okay.
So we are targeting all those things.
Do you need to specify that part? Because we need to search license plates in the middle of the image or lower middle.
Yeah,
Do you train the model for doing this or it's automatically?
it is automatically.
Yes. Can it also perform good if there are 5 different cars? It can detect-
In that tutorial, it's showing that it's possible with at least 2 cars. But I don't know how accurate it is. If it's the best one or not, I haven't focused that much on that. I just wanted to have something up and running that it's working good enough for our example.
So this is important. So maybe if 2 cars are racing, you need to just take pause, right? Because they are in the same line, the same speed.
So it depends on the level.
And I don't think it's trained on Norwegian car plates,
Yes.
but I tested with this car and it worked. So it seems like it's working.
It should be possible to collect data from Norway, but I don't know if it is legal.
I don't know.
I don't think so. I don't think so.
I don't think so either.
You can just go to the party.
Take a picture of 100 cars.
Okay. So thank you very much, Hamad. Thank you very much, Gregor. Thanks for Simon and Vivian. Okay, so it's feasible. You feel that it's feasible. We will be able to catch up by the end of the course, and we will have good results. Good.
We hope so.
Okay. So any questions to the presenters from online? Any questions? Any questions from Leo and, for example, Muhammad, who has been working in the same problem to this group? Can you hear us? Okay, no questions. Okay, thank you very much. So we will go to the next presentation. So the next presentation will be Masoud, or who is ready for it? Who want to present? Ahmed? Huh? You are not presenting today? Huh? Masoud, yes. Masoud, but it's not 11. It's 10. I don't know. Maybe I don't know if he is online or not. Masoud, are you online? Can we check if he is online?
Yeah, you can present, but you don't have phone.
Masoud. No, he is not online. Okay, so we can go to the next one, for example, in the list. So maybe Dan and Ravi. Ravi, are you okay to present now? Ravi, can you hear me? Yeah, okay. So just please feel free to share your screen and present your project.
Yeah, just give me 2 minutes. I'll set
Okay.
it up.
Okay.
You have the algorithm, but we didn't have it in a PowerPoint. So that we have to present the algorithm.
No, it's fine to present the algorithm, but please, I mean, next time try to prepare few slides. So to make it easy for people to, for example, when you run your model, maybe you will have some table of numbers, accuracies, stuff like this, confusion matrix.
Because I already run for different hooks and different type size and make a Excel file in order to
Yeah, yeah.
better to size.
Yeah, it would be if you have some slides, so you can just summarize the results. Okay, we have
Hi.
Ravi
So
and then,
yeah.
Yes.
Hi all. So this is Ravi, and my team partner is Dan. She is also online, I think. So Dan, feel free to pitch in anytime you want. So I'll just present the idea. The title is a bit ambitious. It says vehicle identification system because the initial idea was just to do the car, but we thought since it's a final project, if we are successful with cars, we'll extend it to other vehicles as well. So yeah, the title is kind of tentative. And so what's it about? So we'll sort of ID the vehicle with 4 attributes, that is color, license plate, make and model. The model part, I'm not very sure as of now because it's a little tricky and we need a good data set with labeled data, which I haven't found till date. So I didn't find till date. So it's model part, we'll just leave it for later. If possible, we'll do it. But otherwise, our plan is to do color vehicle identification with its color, license plate, and make. Make because so I picked these 3 attributes because, like in any crime scene or like in any traffic violation, the 3 most important attributes are the vehicle color, its company, its brand or its make, and license plate also. So model is not really that practically useful in forensic or traffic violation investigations as such.
Because also if someone will did a crime or something, the license plates, they use a fake license plate, so they move it, right, or cover it, for example. So color and the make also are very, very important.
Hi, can I continue?
Yes, please.
Yeah. So what do we want finally to achieve is that we want to detect we aim to detect multiple vehicles and show their bounding boxes. And we also want to ID the vehicles and show the attributes which belong to them. It would be something like this. It's really ambitious, like we are nowhere close to this. But it's like, if possible, we would want to do this. Real time, I'm not sure, but maybe with static images, we can give it a shot. That's the desired output. I did it on Paint. This is nothing, I didn't do it on using a machine learning model. This is done on Paint just to illustrate what I intend to do. And so the approach would be to train a deep learning image classification model with a labeled data set, hopefully, with a vehicle type, vehicle color, and vehicle license plate, and a vehicle make. So the data set that I got, so that's the thing we want to do. And right now where we are is we started off with cars, which was the initial idea for the assignment. So that's where we started off. And I only use the model taught in the class till date. That is the MLP classifier. It's a pretty basic classifier and it doesn't really do much, but that's all I know. Currently I don't really have a knowledge on the RCNNs, the other deep learning models that are appropriate for this task. So I just use whatever I know till date. So the data set we have picked is the Stanford AI cars data set. It's a very extensive data set with around 16,000 images. They're labeled. You also have a MATLAB code which can give you the bounding box. They also have the bounding boxes embedded if you know how to play around with MATLAB code. And you also have, it says that it also has labels for make, model, and year. I'm doubtful because I couldn't find the labels. I didn't know MATLAB very well, so I couldn't play around with the code and extract those labels. So right now it's very basic. I mean, the step 1 was what we did so far is. Sorry, sir. Sorry, Ibrahim.
Small question. I mean, this stuff for the data set, is it, does this data set has license plates? It has license plates?
No, it doesn't have license plates. No, it doesn't. It doesn't have license plates. We need to pick a better one for another one for license plates, or we need to move on to yeah, that's right. So this doesn't have. I forgot to mention. This doesn't have license plates. So we need, once we are successful with the color and just get the feel of this classification, we may have to move on to a better one. The ones probably Leo and Mohammed are using, or the other team is using. But for now, I started off with this AI dataset because it has got a lot of images, and I thought uh, it'll be helpful. But yeah, license plate is that data is absent in this. Can I move on?
Yes, 1 minute, please. I mean, this data set is very good, in fact, because we can use this one for captioning, image captioning. We can describe it. So when we're studying RNN, for example, we can use this one for getting. We have this one for sequence. So you have the input will be an image, and the output will be a description of the image. So the description of the image, it could be all those informations: make, model, year, color, and all those information. So for example, if someone did a crime, for example, we have a system enrolled. It was just to give you a short description. So the car was blue car, BMW 20, for example, 2015, for example. So we can get the caption, which describes the image. So we call it 1-2 sequence. It could be one application for RNN, for example, using this data set. Yes, Robbie, please.
Yeah, that's right. So so as Ibrahim mentioned, we can use the labels in a lot of applications, but I'm still figuring out how to extract the MATLAB. There is a small MATLAB development kit on the website. So you can go to this link and you can download the images as well as the data set or the development kit, which you can use to extract the bounding boxes, the labels, of make, model, and year. So so what we have done so far is it's a baby steps approach because I started from ground zero. I didn't really have any background in ML. So I've started with car detection, which means that I'll train my model for cars. So if I show an image, a test image to my model, it'll be able to tell if it's car or not. It's a binary MLP. It's very basic. So step 2 is I finished step 1 with like a reasonably okayish accuracy. I don't want to like it's very poor. I'll show you in the next slide. The color detection, I have an idea, but I want to discuss this with you and put it up on board and maybe receive your comments and criticism. So I'll move on to step 1. That is the car detection. So we built a basic MLP to get a feel for, this is only to get a feel of image classification. I haven't really done this before. This is the only experience I have is the MNIST dataset that we solved in class. So I use the same concept here, and I haven't really done any of the RCNNs or any other deep learning models. So we've used around 200 training images. 100 were positive and 100 were negative. 100 negative is, I'll come to that later. So the 100 positive images are the images of cars, and the negative ones are the ones of other objects, just like not cars. So I'll tell you why I did that later on. And 64 were test images, 48 were positive, and again 16 were negative to just test how my model performs. So that's the confusion matrix. And I'm sorry for not labeling it really well, not putting the plot labels really accurately. So what it says is, so 38 cars were predicted as cars. So that's good. And 8 non-cars were called out as non-cars, which is also good. But 9 cars were called out as non-cars, and you can basically see what happened. So the accuracy was around 38 plus 8 divided by 64, which is around 71.8%. It's like really poor. But it really helped me get a feel of image classification and MLP and whatever stuff that's taught in class till date. So I'm really comfortable with MLP at least by doing this small exercise. And a couple of notes to point out is I tried to add more images to my training data, but that didn't really improve my performance. It only the iterations were, it was not converging, either not converging, or it took too much time, or it just didn't work. So 200 images was fine, but anything more than that did not really help me out. And adding negative images was crucial because like when I did not add negative images, when the images were only cars, when I showed a picture of an apple, it said it's a car. When I showed a picture of a computer, it still said it's a car. So I learned that I also need to teach my algorithm what is not a car as much as I need to teach it what is a car. So that was the negative images part. And yeah, so for color detection, this is my strategy. This is again a very experimental, very rude, whatever, like, so I want to use my same MLP and the weights that it gave me to sort of understand which pixels are important and which pixels aren't. All the pixels which contribute positively to your first order features, which in turn contribute positively to your second order features, and which contribute to your final car are super important pixels. But pixels which contribute sort of negatively somewhere and, you know, which really don't, which have negative weights, I think are not going to be useful. So I'll only sort of glean out those pixels which have a positive relationship, and use this to understand what the color of the car is. This is again it's experimental. I'm not sure if it works. It's a little tough to build this data structure also, but I'm just like figuring out how to do it. So yeah, it's a long way ahead. I mean, so we have to use, I know that we need to use more sophisticated algorithms like the RSNet or the GoogleNet that Nicholas pointed out, or the mask car CNNs, which Mohammed and Leo are having a good time with. So I probably need to switch to them. But yeah, so what we need to do is detect the objects of interest, that is detect if there's a car in the image, and then classify if it's a car or a truck or a bike, or you know what kind of vehicle it is, and then subclassify the image if, you know, based on its make and model, and then sort of do the semantic segmentation of the license plate and its color. So we are planning to sort of like do all the tasks independently and then cluster them into one master ML algorithm, which can sort of like do everything. Again, it's sort of like everything in the conceptual stage. I haven't really touched or experimented with some of the sophisticated algorithms yet. Yeah, that's pretty much it. It's a very short presentation.
Okay, thank you very much, Ravi. Thank you very much. You are using the talk now. You are learning Noshki. So
Yeah, exactly. That's right. I'm learning machine. Yeah.
So this is very good. So I have some comments. Do you have any comments to Ravi? Any comments to Ravi? How to improve his model? Because the model now is accuracy is 70-something%, and it's binary classification. It's car, no car. So is there any way to improve? The image size is how many? The image size is 2,500 pixels, right?
Why he has to do it again if something is already present? Like
Because he need to train his model from scratch, because it's a learning process. So you want to do it from scratch. And he is using a MATLAB, and he used the 2 hidden layers, one hidden layer and one output layer, correct? It's 2 hidden layers, correct, Ravi?
Correct, yeah. That's right. So I'm using like whatever you taught us for the MNIST data. I'm using the 100 neurons in the first hidden layer and 30 in the second. And yeah, it's like, so the same thing. It's just that your MNIST had a 10 class. It's a 10 class problem. This is just a 2 class problem. It's like
what is the image size? What is the image size?
500 by 500.
500
pixels by 500 pixels. That's right.
So this is huge. In fact, this is huge. Not all pixels are important. So I just propose that you need to try to use, for example, PCA, principal component analysis, right? So we can select the most important pixel features or descriptive features, because now it's huge. You don't have big data. I mean, you are using 200 images for training your model, but your model is really very complex. So it will be impossible to use this small set of images to train your model. So I suggest that you compress number of features maybe to 100. So we need to use principal component analysis to select a small set and reduce the set of features instead of using this huge number, right?
So you want me to like resize the image to a smaller size, or do you?
No, I mean this is the size of the image. You have 25,000, correct? No.
Right.
No.
Correct. Yes.
Yeah, so this is huge. This is it's too much because you have 200 images. You have only 200 images. So with this small set of images, it's impossible to train a model with such kind of complexity in fact. So it will be too tough. It will be underfitting. And that is why you cannot improve accuracy because it's underfit your data because your model, it's overfit, sorry, it shouldn't overfit in fact, not underfit. So I just propose that you try to use BCA, principal component analysis, to get a reduced set of features. So just select the top 100, top 100, principal components. In this case, you will simplify your model. So maybe you can get better results.
Okay.
Right?
So this principal component analysis is so I need to tell my model what features are important, or it's going to like learn on its own.
In MATLAB, it's only one line. It's called the BCA. BCA. The input will be the image, and the output will be the reduced image. I can call it XR, for example. And you will select here how many principal components. So just to try search BCA in MATLAB. It's one line code.
Okay.
So this is very, very important to use principal component analysis and use a reduced set of features instead of using the full set of features, because this is very complex. Your model is very, very complex. Just imagine how many number of weights we have. So if you have huge number of weights, we need more data, and you don't have more data, you have only 200 images.
Yeah.
So this is point one. We need to try principal component analysis, right?
Okay, so is this available in SK, Scikit or such things? Because I'm not using MATLAB for my.
Yes, you have MATLAB. You have one command called PCA in MATLAB. The input
No. I'm not using MATLAB for my my training. I'm using Python itself.
Python.
Yeah.
So it's the same.
Yeah.
Python, you have PCA in Python, correct? Yeah. It's called the solver or something.
Okay. I'll.
We have an sklearn. We have BCA from sklearn. I used it in some examples. You just go back to the slides and you find it.
All right.
Yes, you can search the package named as sklearn. It includes PCA functions in the sklearn.
Okay.
Sklearn. Okay. Okay. Thanks, Mangitao. It's great to have you with us. Yes. Because we need your help in this part in this part. So first BCA. What is there any other points? Did you scale your data? Did you normalize?
Yes.
Okay.
Which would be basically like do the make it between 0 and 1, right? That's what you call. I mean, divided by 255, right?
Okay. In MATLAB, we have AlexNet. If you are using MATLAB, we have AlexNet. You need to use it. It's a pre-trained model, and it's very good for classifying very complex problems. I guess it's 1,000 objects, so you can just use it to predict if this is a car or no car. So you need to try AlexNet, for example, right?
Okay.
I mean, for your data set, you need to show more about the data. How many colors in those? You have 1,600 images, correct? 16,000.
Yeah, that's my that's the entire data set. I'm only playing around with 200 images.
So try for this data set to list how many colors you are targeting, how many different types of car model and makers and stuff like this. You need to analyze your data a little bit more.
Yeah.
But you are on the track and you are just you are on the
I can
track.
show you folder of the image. I can maybe stream the. Just can't figure out how to do this. 1 second.
I mean, AlexNet, it works in real time. You can just, when you install it, when it sees the image, it will just classify it in real time. It will draw bounding box around each object in the image, and it will classify it. So you can have multi-objects in the image. For example, you have a computer, you have a cup, you have a tree, you have a car, bike. It will be able to classify all those images, all those objects in the same image. It has been trained using AlexNet dataset, I guess, which is millions and millions of images. So it's a very, very smart AlexNet.
Okay. Yep. So like I said, it's I'm like really at the ground zero. So I'm slowly we are slowly learning. So we'll get to a better point next time, maybe when we have a presentation.
Yes. Yes.
We'll improve our accuracy maybe by 1 point.
No, just to try principal component analysis. Maybe it will help you to improve accuracy. Maybe also Mengitao can say something. Or do you have any suggestion? How can he improve accuracy? You need more data. You cannot use only 200 images. If you have 16,000 images, you need to use all images.
Yeah,
So,
that's
I
right.
don't know-
But like,
I don't know how many images has car, how many does not have a car. So you need to check. I mean, your data set. You need to check your data set. And try to use more data. Try to use cross validation. I mean, now you divided your data into one for training, one for testing. Maybe this is not correct because your data set is very small. So in fact, you need to go for cross validation, right? Eightfold cross validation. You divide the data into maybe a number of folds, use it for testing the model accuracy, and after that, use the whole data for training your model. Yes, increasing the hidden layers. And,
How many?
no, he's not using CNN. He used straightforward NLP. He used NLP. So he has 2 hidden layers. So just to try to reduce the set of features instead of using the whole set, because the whole set, the model will be really very complex. And when it's more complex, you need more data to train it. Otherwise, it will underfit. Right? It will underfit because you have only 200 images. It's not enough. If you have this huge number of, he used in the first hidden layer 100 units. In the second hidden layer, he used 30. And of course, in the output, we have 1. And how many inputs? It's 25,000. So just imagine number of. So this one would be the number of parameters of the first layer. This one, it will be 100 times 30 plus 30. And this one, it will be 30 times 1 plus 1. So you have huge number of weights. This big number, it's more than number of data points. So the data point which we have, it's not enough for training your model. So just try to simplify your model a little bit. Try to simplify it to have, so the data set will be more or less comparable. But so try to use BCA, for example, use the most important 50 features and try to test it. I'm sure that you will get better results with using BCA.
And there is a library in the Keras. I don't know that the library is his data or not. In order to augment his data, flow underlines from data frame, and he can use in order to augment the data, and maybe the result could be better.
For augmentation?
Yes.
Okay.
Because his data is not enough, I think.
He has
16,000 images.
He has 16,000. He used only 200.
It's not enough.
So you need to use more data, Ravi.
Please try flow underline from data frame in order to augment your data. Maybe your result will be better and nicer. Yeah.
So in fact, there are lots of big room for improvement, Ravi. So yes. Any questions online to any online questions to Ravi? Any questions to Ravi? Okay. So thank you very much, Ravi, for your project. Yes. So we will go to the next project. So the next project will be Masoud. Do we have Masoud online? Amir? Amir, are you ready? Okay. So Amir will present because we don't have Masoud online yet.
But I also don't have many slides because
yeah, it's fine. Yes, because we need to know the status of each group, for example. So we need to know if it's feasible to finish the project by the end of the semester. If you want to write a paper or something, you can do it after the exam, no problem. But now, at least we need to check that we have good results and making progress. Can you share your screen? Okay. So Amir, Bedar, and Andreas, they are using machine learning for facial recognition.
Okay, so my name is Amir. I teamed up with Andreas and Peter. And at the beginning, like everyone else, we wanted to try with the license plates. So I will explain that part a little bit. We used a mask RCNN algorithm which I think is a little bit maybe too complex for license plate detection, because it also creates a mask for the license plates, which you don't necessarily need. And I can, if you want, I can show also the code. Maybe. To use this Mascar-Sinan algorithm, and there is actually, I don't think there is a library that you can import. So
Is it possible to change the background into white color, or it's
Then you can turn off
huh?
the lights.
And
Turn off them. Can you turn off the
is this the light?
Yes, I'm just used to PyCharm.
Because the light is for the whole.
You can change the.
But no problem, and it's okay for me, no problem. Okay. Now it's much better.
It's better. But there was something, I don't remember that. So this is the main, because you have to clone the GitHub repository in order to use Mask-RCNN for now, because I don't think there is a library that you can use. But this is the main model, and as we can see, it uses several blocks. The first is identity block that uses several filters. And the second one is convolution block that also uses several convolution filters. And also, all of this is used in a resonant graph. So all the data also goes into this block. And in this resonant graph, we use that identity block and that convolutional block in order to process the images. But this is the very long algorithm, so I must explain the whole algorithm.
But what is the need of RCNN? RCNN? What is the difference between RCNN and the mask?
Mask-RCNN also creates a mask. RCNN also just creates this bounding box. But Mask-RCNN also creates a mask.
Okay, so it creates a mask.
I will show the results.
Okay.
So this is my code. I just use this Mask-RCNN, and I use the COCO dataset pre-trained weights.
COCO is for what?
COCO is just different. It is short for
Microsoft Cocoa?
Yes, common objects. I don't remember, but it's a combination of all objects, like cars, trees, buildings, everything. Okay, this is the configuration. That's how many GPUs, how many images per GPU, how many steps. The most important thing is to configure our dataset with the algorithm, because it has its own class that you have to configure for your own dataset if you want to train the algorithm on your own dataset. Because you also can just use it to pre-train for weights. But if you want to train on your own algorithm, you have to configure this class. So I used, I added a new class, which is for license plates.
Are we adding one class to the original dataset? This Microsoft Cocoa?
No, it's not Microsoft Cocoa. It's my own dataset that I downloaded.
How we call it?
Yes, that's why I added this new class. It's for my own dataset, which consists of, I don't know, 420 images maybe. And I iterated through the directory, and I use 350 for training and the rest for testing. And here, because with that dataset also came XML annotation data. So here I parsed the XML using this element tree. So we iterated through the XML files to extract the xmin, xymin, ymin, xmax, and ymax to find these and put it into this array. And also the width and the height of the image extracted from the XML files. And this part is for the algorithm itself. So the most important part is just extracting is to adding this class of your own dataset to extract the image and the annotation. And then we will use this train set. We will use the class, the database class that we made.
For annotation, you did that for the license dates? You did that, or it was that already?
No, it was the XML files, but were ready.
Okay.
But you could do it yourself and extract the XML files, but then also you have to do this.
And in case of RNN, we don't need to scale the image or.
No.
Yeah.
And here we also don't need to scale the image. Yes. And we use this class for our train set. Just we have to use this train is equals to true. So it knows that we use this for training. And for the testing, we just have to use this train equals to false. So it knows that we use that part for testing. And we initialize the model in the training mode. And here we can use the pre-trained COCO weights, which I downloaded in my local hard drive and use this for initialization.
So one more time, you used RCNN. Did you change anything in RCNN? Did you?
This dataset part.
Yeah,
I had to customize my dataset.
Okay, but this one we will not train it. This mask RCNN we should not train. Simply train.
I trained it on my own dataset, but I just used the COCO for initialization.
For initialization.
Yes, just for the beginning.
Okay.
To start from that. Because it takes so long if you just want
Yeah, it's a transfer learning, but sometimes we just freeze that part. We don't train those weights at all. And we have, for example, in CNN, we have fully connected layer, which will be trained. So we will not train the top, the feature extraction part, but we will train the fully connected part. So here you are training, but you initializing it from COCO.
Yes, just for initialization.
So he's trained like the fully connected part. Now he has used the weights for the pre-trained the model for the COCO data set. And he's going to start from that, from those weights.
Start from those weights.
And retrain again the model using your data.
Yes. What is started from those? So it's just converts class.
Okay.
And in the end, I just saved the weights that I received from my own dataset. It took like few hours train. And I just tested on random image. Let's see. It wasn't very accurate because I just used like 5 epochs. I had to use more.
Now you are testing, you are not training.
Where it is.
You are testing.
Yes. Okay, I have to share this. So this is the result of the image. As you can see, it also created a bounding box and a mask to mask the plate, which I don't think we know. We need for license plate detection. It's too heavy for license plate detection.
But now can you convert this one into text? EWWPO. Can you read it?
Because we were discussing yesterday and we decided to change actually the topic. So I didn't spell down on top.
So now you just use the RNN for masking. But not.
But we can just use RCNN. Or we can use that YOLO, which is pretty much faster.
So maybe I just want to ask a question. Maybe, for example, when you are using YOLO, have you retrained again the model using the dataset, or you just use it directly?
They already have a variety of objects already trained for that.
So you haven't trained again with the data.
No. I used the pre-train. So I just loaded some weights already trained
Okay.
to detect the car.
But
So that
you know this
For that part. So the only thing that I trained on that was after you segment out the characters and numbers, then I was training on a data set with characters and numbers. So the first part with detecting the car and to get the license plate, I just use a pre-trained module. So it's just the second part that I really actually went into the machine learning part where you're training.
But please share an example with me using Euro, so I can add it to just one example using Euro for plotting those bounding holes for any object, maybe any other data set also it's fine. Just maybe you can make some.
I think then I should go in and see if I can find an easier example.
Yes.
Just
Share it.
do it myself and then I can say.
Okay, so we can make some few slides about those nice pre-trained models. You know, this ResNet 16, which Nicola used today, for example, and also VGG 16, which is used in this moment, and data. Okay.
But if you don't want to train an own model, we can just make like this start and just load weights from the COCO.
Yeah, because when you configured it, you put training, you will retrain it. So I'm just worried if you will retrain it, you will damage the weights, right? Because we will just update the weights.
No, because maybe we want to just use it in Norway. So you can train in with Norwegian cars. So you can kind of customize the weights.
Yes. So this is a very good example. Thank you very much, Amir. So any questions? Any questions to Amir? Any questions? Any questions online to Amir?
Maybe you can dig into the COCO and look into which layers we should freeze and which layers we should freeze.
This is the question. Yes. Which part should we freeze? We don't retrain, and which part we need to adjust?
Because you can freeze the layer.
Yes. But actually, we decided to change our copy to face recognition.
Yes.
Have you decided on which type of network you're using
for face recognition?
Yeah. Have you looked into it?
I found that.
But we want to use this open set. So we want to, whenever the model will detect a new person which does not exist, he will create a class for him, which is this is very important open set. I mean, for example, if you are building a system or building a security system or something, it must be open set because all time there will be no one who will need to give him access or something.
Like for face recognition, also we can use this VGG system.
Yes.
Which is popular for face recognition.
Yes, but please try to go for this open set. Remember, it's not binary classification. He is a human, not human, male, female. No, we need to have this open set. So we will have number of classes equal to number of persons.
But we still need some pre-trained model to detect the faces.
Yes, and maybe some faces at the same time if you have not.
So we can use this VGG system for face detection.
Yes.
Do you think like the model would have maybe the results would be like less accurate if they haven't pre-trained, for example, the model what they have used using the new data set, if they have just applied it directly?
No, but maybe the accuracy will be much less because we don't have enough data for training a model from scratch. So using those pre-trained models will save huge time for people. Because those models has been trained by Microsoft, Google, for example.
But it was trained for all the objects,
all
objects for license plates, so it wouldn't be.
No, my question is different. I said like, could we have used it directly without? Because he said that he has used the data sets again to train.
Yes, because for example, for face recognition, those models have been trained for other objects, maybe for cups, cars, umbrella, tree. So we need to customize it to a new object. I don't want to classify into cups and computer. No, we have certain classes. We have one class, human face, for example. So we need to focus only on this. In his project, he will use this open set. So each time there is a new person, he will add a new class, right? So we need so number of classes will not be fixed. So this week we are 5 working here. So all of us will have access to the building. Next week we got new one who will be joining us. So we need to create a new class for him. So it's not a simple problem, it's a good problem in fact. But just try to focus on this open set case recognition problem and try to search literature review for it. It's like in our classroom here, all of us have access to the building, to this room, for example. Next semester, maybe after next week, someone joining us. So we need to add them to the list. So we need to create a new class for him. It could be unsupervised, trying to figure out how we will solve it.
As you can see, Coco has
No, we have worked with Mengtao on the exactly these data sets. We have used Mask RCNN with Mengtao, and we have used for the Moroccan plate recognition, it was done by somebody in Morocco over there. And we have used the same technique actually, but I was just asking to know the reason why do we use again our data sets for already pre-trained models. So you said to customize it.
If it is the CNN, I don't know, or in Mengtao? Are you online Mengtao? Maybe Mengtao can add something.
Yeah.
Because also in our yes, Mengtao.
He's here.
I saw a picture yesterday for online learning. Someone, I mean, the tablet was just teacher was just teaching, and a child was just sitting on the sofa and sleeping. so this is my learning. So some people just, I mean, keep it trying and be online, but so I need to know how, because I don't have that much experience in art. I need to know. It's
RCNN is a subset of CNN.
No, this is regional convolutional neural
Yes,
network.
regional convolutional neural network.
So it is CNN.
CNN.
Yeah, RCNN.
Okay, sorry.
Regional.
So in this case, the part which will be responsible for feature extraction, we don't need to retrain it because it's very complex. We just need to use it as it is. The only one which will be trained is the which will be used for decision making.
So in this case, they could have like used the data set directly on the.
No, but you need to use features. So you have a block here, which is RCNN, right? This one will be dealing with feature extraction. You will have an image here. You will get some higher order features or high level features or something here. So here we need to flatten it, and after that we have some fully connected layer for making decisions. This one, it's initialized by random values. So this is the part which we will train that part, but we will not train the part. We will train only the. You have the option to train and use your data set for just training the whole model. When you're training the whole model, those weights will be the only weights which will be trained, but not that one. We don't need to touch that part because this one has been trained using millions and millions of images in very powerful GPUs. So if you will train it, you will destroy it. So just worry in your application here. If you will retrain that part, maybe you will damage those weights.
I think the model takes care of it itself because we just configure our data set.
But you didn't plot the confusion matrix. You don't know what is accuracy, right? So you need to plot the confusion matrix. You need to try first without training the part, and after that with training. I'm sure that the accuracy will be less. It looks like okay when we see it here in some examples, but you need to see the whole image. Okay. Just imagine this one is very complex. It's like VGG 16. It's 16 layers. You really have enough data to retrain those? Because you have only 400 images. It's not possible. So if you will train the whole model for 5 epochs, I'm sure that you will destroy the weights which have been trained. Just use it as it is. Don't touch it. You need only to train the fully connected layers which are responsible of decision making classification. We use this one as it is, so just for feature extraction, because this is something common between all images. If you have image of car license plate, fine, it will be fine because the most important to us is to extract some features here. We will use those features for decision making. This bot will be in charge of the decision making process. This is the one which we need to train or build, right? Because here we will initialize weights by random values, and we will train it using the small data set which we have. But we don't have enough data to train this one. Don't touch this one, right? I don't know RCNN how many layers in RCNN. How many layers mass RCNN? How many layers? It's called the mass RCNN.
From the link.
Okay, I need to check it. How many layers? Someone is making noise. You can mute your mic.
Yeah.
Are you making?
It doesn't look like he's fighting.
Huh?
It doesn't. He's fighting, wrestling, something like that.
Yes. So sorry.
Exactly.
Yeah. Okay. So we can go for the next presentation. Okay. So thank you very much, Amir. And we will go to the second presentation. The second presentation will be and Andreas or Masoud, who is online?
We're together.
Okay. Okay. So Amir is done.
Oh,
Amir Khakan.
no, there isn't.
Mahdis.
He's another Amir.
Okay. So the second Amir. Yeah. So please just feel free to share your screen. Okay.
Can you see my screen? Hello.
Hello. Can you increase the volume of your? We can hear you, but it's very low. Can you increase the volume of your mic?
Is it okay?
No, we cannot hear you. Please, can you try again? No, we cannot hear anything. Mahdis, can you maybe change the mic or use the computer mic or something?
Okay. Is it okay now?
No, it's not okay.
Not okay. Okay.
Okay, I will try to increase the volume here. Mahdis, no, we cannot hear you.
I don't know why.
Can we increase the volume here? Can we increase? No, in this one we cannot control. Mahdis, we cannot hear you.
Okay. Can you hear me now? Professor?
Huh? Can you write to here to increase the volume? We can hear you, but it's very little. Yes.
Okay. Is it okay?
No, not okay.
Not okay? I don't know why. The volume is high.
Hello, this is Hu. Can you hear me now?
Yes, I can hear you.
Now the voice is clear.
Yeah, it's clear, yes.
Okay. Mandis, could you share your screen because the presentation you have is the latest, so I can, yeah, I can
Yes.
set, I can.
So someone can share slides and the other one can just talk.
Yeah, yes, because I'm not have the latest presentation. Yeah, switch to the first slide. Let's start. Yeah, our group is made of the Amhad, Madis, and my name is Zhicheng Hu. And we have the two topics about our group. The first one is car mode classification. We wish to focus on this one. Also, we do some project about the license plate recognition. Let's have a break about the first one. This one I have sorted we have the reported, delivered, and the main task is split to two of them. The first one is we use the Kaggle dataset. We used one existing model to go the whole procedures of the car plates recognitions. And the second one is we use the Mask-Gaussian to do the car plate recognitions. And we find that yeah, maybe some the hardware is not so good. So the runtime is yeah, it's so long. Today I just fixed my problems about collapse, so we will do this later. I also asked the Leo and another guys about the repeat epochs numbers because I run only 20 epochs, so the result is not so good. But they around maybe the 60, so I wished to add some the epochs numbers, maybe have the better results. So about this part, we wish to in the next 2 weeks continue to do some more works. And maybe Manis, could you quick share my report? Open the report, please.
Okay, thank you very much.
Yeah, I have one report. Quickly review, then we go to the next part.
Okay. So you will share your screen.
Maybe the Manis could you, I have sent the report to her.
Mm-hmm.
Yeah, Manis, could you open your report, or maybe later I used myself because otherwise we have to switch the presentation. Yeah, okay, I can. Yeah, yes. And this one is the report, and also in this report, yeah, go to the next. Yeah, go to the next. Yeah, the first one. Yeah, wait here. Yeah, please. And here, yes, we can see that the comparison of the annihilation of the regions. And the left one is the test result. The right one is the original mask. I just pick one pictures, and also the yeah, because we have to reshape to the 224 pixels rectangles, because we have seen that the origins of these images are a bit different. Yeah, and go to the next. Yeah.
Okay, so all images has been reshaped into 224 times 124.
Yeah, all the images have the do reshape to these pixels, because we go to the first page. Please switch to the first page. Here have all the inputs and models, some statistics about this part, and the output is about the XY rectangles for an error, because there are several place regions in some images, so it's an error. Yeah. And then we go to the next. We will find that some used OpenCV like other guys used, and the split to the several characters. Yeah, we go to the go ahead here, and split like others. And now the result is here. But we have to mention here because the conclusion, yes, we find that maybe some pictures is not very clear. So it's for example here the M is wrongly to recognize as the character N. A lot of similar like this, and sometimes when there are several plates on the image, it failed to recognize even one plate from the images. So yeah, we still have some improve about this part.
Okay, so they went to the next level. So now they can convert it into.
Yeah. Yes, we wish to.
What model? What model did you use?
Yes, because here we are not trained. We used to pre-train the mobile, not train too much. Yeah, and the second part is about the use the mask RCN. RCN we supported by the Mentao, and he gave us some ideas and one link about the car plate recognition, and also together with the balloon data set. So we compared the data set. Here, go down. We will find that the format is a bit different. So I have the write a small code package and go down, please. And finally, convert the XML file to the JSON file, and it's a familiar format. And after that, we can use the mask RCN better. So we run this data set, and go down, please. Yeah, and here, this is our data set from the Kaggle, and go down, please. And here we have the split three sets, and use the license plate file, and the learn rate is about the 30.1 and default, but the result is not so good. I guess it's maybe you can see the red rectangle. My poor hardware, for one epoch it cost 1 hour at least. So I run 20 epochs, so not so good. So we will push this more time, more epochs. I guess it will work better. Yeah. So it's just a brief talk about the car license plate, but we pushed much more time on the car model recognition. Yeah, please switch to the PowerPoint.
Okay, yes. Okay.
So the recognition, you have the recognition part here. So they have the recognition part. They did that.
Yeah. Our main focus is the car model recognition for the car model, and the car plate is just a part of this.
But the license plates, now you can recognize it. You can convert it into a text and the digits, right?
Yes, but the result is not so good because
what is
the characters? Yeah.
What is the accuracy? What is the accuracy for each example also? Because I can predict one example with 100% accuracy, the other one 80%, so I can discover almost. Yeah, actually, I'm not absorbed all the codes because now I've tested the images one by one, not the batch to stabilize the accuracy. So for your team, Ahmed and the Bjornar, is there anything here which you are missing? For example?
We were actually using that one, so and that tutorial that he had done also, and then you're giving out the numbers. But as he says, probably if you have tested with several images, then it's not that accurate.
So what is there are two types of accuracy? Maybe we have an accuracy all over accuracy, correct? And accuracy within each car. So I can predict your car with 100% accuracy. I can predict, for example, a new car with 80% accuracy. So I have an error in one digit or one letter, for example, right?
Yeah.
So just meaning, I mean this kind of accuracy. So you can have two types.
Well, yeah, we can calculate it later because the data set is only have the region annotation and not the character annotation. So we have to manually label it by ourselves. Otherwise, it's impossible to.
Is there any pre-trained model for this character recognition? And there should be something, right?
Yeah, it's only have the coordinates. Yeah, no characters.
Recognition. OCR is very accurate.
Yeah, and then we go to the. So can I continue?
Yes.
Okay. Okay, so our main focus is about the car model classification. We use the dataset from the Stanford car datasets. I see that the Ravi group is also used this dataset, so I'm not explaining too much about this part. And we found that there are several ways and some papers about these models. It's not easier directly use a simple deep learning network. So we compared the several ways. For example, we used here the simple CNN. The result is very poor, and we also see some proof from other some papers. So at least we used VGG 16 applied. So, but it's also the problem about the runtime. Now we have fixed today, and we wish to run more epochs because we see that in some papers it even should be around 50,000 epochs. It will work very well. So, yeah, we will evaluate which ways is better. And we found that today, like today, other groups that use the residual network. For example, here we also at the mobile net it will much later to run the data sets. So we wish to the future to get better. So let's see have some results. Yeah, please go to the next slide. Yeah, here is the total. Too fast. Here. Here is the result of the run epochs after the 100 epochs, and the accuracy is still very low after the calculation. And Matis, could you go back the slide about the structure? Yeah, here have the structure. We have seen here we used the VGG 16 and delete the top layers and use the weights of the image nets, and we add the only one dense layer, and the second one is output, and also use the dropout. So it's very simple. Now I'm also calculating more dense layers, which to have the better results. This is the structure. Yeah. And we go to the next. Yeah. And also we use the one simple CNN, and here is use the input. First we have to reshape to the 256, and then we have the several layers, and we use the flatten and one dense. Yeah, here. But I think here you have some problems discussed with others. For example, the layers, the third layer, you can see the dense number. The dense number is the 64, but the output is nearly 200. So normally this dense layer number should be larger. For example, later we used 512, and then drop out for example, 50%.
I mean,
so
this 64, you can make it 256, for example, right?
Yeah, but here it's not a very good result example. Yeah.
But in this one exhibition here, I mean this is a filter size 3 times 3. I mean the input image it's RGB image, correct?
Yeah, RGB image. So we have to reshape it. Yeah. Go to the layer 1. Yeah.
Is it correct? The filter here, is it correct? Is it working without any problems?
It's also have some reshaped procedure, not print here.
No, I want to check this one.
Yeah. Yes, you can see the layout 1. Yeah, the layout 1 is the input shape. It has been reshaped. It's RGB. Yeah. And some, for example, we find that the layer, the last layer, it's better. We use the softmax.
I'm just asking, just one minute, please. I mean, in this layer number 1, I mean, is it correct? This one?
This one is correct, but the previous, because the data set is different dimensions.
Okay.
About we have to reshape the first to the 256.
The size of pixel? 3 times 3. Okay.
But because the image is RGB, So should we use here 3 times 3 times 3 or just 3 times 3? Should we, what kind of filters should we use? Because this one will be applied to the input image.
That is fully connected or
No, this is convolution.
That's the kernel size, you mean?
Yeah, kernel size.
How it can understand that it has 3 layers?
Because here it's a 3,
Yeah.
right? So it's
This is RGB. Yeah.
So is it correct? So can you please test this one? Did you run this model?
Yeah, we have run this model, but the result here is not good. So we improved the parameters. It's a bit improved, but still so poor. So we switched to we find that some papers said the baseline about the traditional CNN for this dataset is not so good. So we
try to fix this kernel size. Select 3D kernel size here. 3 times 3 times 3 for example, because you have RGB image, right?
No.
Yes, Mingitao. Is there any problem in Mingitao?
Yes, I think this part is correct because in a 2-dimensional convolutional layer, it can process the RGB image. That is no problem. But one of my suggestion is in the layer 4. Why do you use the sigmoid function? Because sigmoid function is used for binary classification. And here I saw you have around 200 output.
Yes, I have stated that it's a not good example. We have changed the later, used the softmax, and also the loss function we changed to the cross attribute.
Yes.
Because it's binary, I mean the loss function is binary cross entropy. So if you are using this cross entropy, this one should be softmax.
Yes. So it's the wrong set about this part, and also I say the numbers are for the layer 3, and I think it's the number is too small because the last layer is near 200. Yeah.
I mean, it should be like pyramid. You know, when you fit the pyramid, it should be like this one. Yeah. So this one 996. This one should be 256, for example.
Yes, at least because we also have some dropouts. Yeah.
So the kernel size, is it correct?
Kernel size is correct because he's using convolutional 2D. This 2D convolutional layer. So you will use this one. You will apply this one to the 3 features.
Okay. Okay.
Yes. But if he is using maybe convolution, is it possible to use here conv3D, for example? Mingitao?
Yes.
Is it possible here to use conv3D, for example, as this one should be 3 times 3?
Yes. I think it should be 2D because normally we always use 2D convolutional layers to process the 3D image. That is no problem.
Yeah.
I can send you some of examples. 2D.
Yes.
Okay, so we can continue. Yeah. Can we continue?
Okay.
So go to the next slide, and here is some results about the module.
But also max booling. Can you go back again, please? Because max booling it's 3 times 3. So do you feel that we will lose? Maybe we are losing too much information when we are using max booling of this size. Correct? See, when it's max booling size is 3 times 3. I mean the image will be shrinked a lot. So maybe I don't know. You need to try those. All those are hyperparameters. I mean, this max booling 2 times 2 it's fine, but when it's 3 times 3, maybe it's shrinked a lot. So you need to check. Okay, so we can go to the next.
Okay, we can see here the accuracy and the loss is not so good also, and go to the next. Yeah, this is some results. Yeah, we have some images of the predictions of this because
I mean, in such cases, try to plot the confusion matrix because it will help us to know classes as being correctly classified and so on. So it's a smart to have. I mean, it's one line of code if you want to plot and the confusion matrix. It will be easy for us to understand the accuracy.
Yeah. Yes. Okay. So yeah. So I think we find that the car model classification, this issue is more challenging. So we wish to push more time on this, and also with the parallel the car plate, license plate recognition. So that's our report. Yeah. Maybe other guys can support me.
Yeah. This is very good. Thank you very much for the good work. And thanks Megitao for helping this group.
And also the Mantis, and also show the some codes on the there's also some reports on the collab.
Oh.
Yeah, you can see here. You can see here have changed to the sigmoid. Yeah.
But also, I mean, your data set is very small, so try to go for cross validation and not hold out validation, because hold out validation and the data set is anyway very small. So if you can maybe also try to cross validation, it will be much better.
Yes. We can try later use the cross validation. Because I also discussed with our team members. There are too many classes. Although the image size is enough big, but the class is too much. So it divided by the 200. It's only
If you can plot the I mean, if you want to see lots of information about your data, just plot confusion matrix for the data also, for the data itself, right? So you can know how many in each class, right? Because I know how many items, how many classes we have. 196 classes. So if you want to know how many images for each class, just plot the confusion matrix for the whole data. It will give you also good information about the data.
Yes. So we also find maybe another way to change a better data sets. Yeah, because you see here the accuracy is too low. So if we draw a confusion matrix,
also, it's very, very important when you are training. You need to plot the accuracy and maybe loss for training testing validation, because it will help you to see if you have some overfitting problem or something, or underfitting. So I mean, plotting those curves, it will be. I used to plot those curves in the last 2 weeks. So try to plot. It's just a bunch of lines. Just copy and paste it. So when you train your model, you need to history equal model fit. So once you have history, you can just copy that part and it will plot training and validation and accuracy and loss for training and validation and testing. It will be very, very important to discover if you have any problems regarding overfitting or yes. So thank you very much.
Yes, thank you very much.
So any question? Any question to this group? Any questions? Any suggestions? Yes, online. Any questions to this group? Okay, so thank you very much, and just keep the hard working, and maybe we will have another, maybe after 2 weeks or something, we can have another project meeting where people can present the status of their progress. So now we will go to the last group, I mean last project. Masoud, are you online? So I guess he is not online. So is there anyone who didn't present yet his project? We are just missing Masoud, who was supposed to present something today about, I mean, breast cancer segmentation using RCNN. So can we say that we finished today for project presentations? Is there anyone who is online or in the classroom who did not present? None? You did not prepare anything? Is there any other people working with you? Soshan, yeah. Soshan is not here also. He is. Soshan, are you online?
Yes, he is not online. So, but please, when we have presentations, you need to prepare some, just at least say something about your project, because it will be very important to get some feedback from other people. And also need to be sure that all people are on the same page, making good progress in their project. So even if you don't have some results, you can just present your what is your project, what is your project. Can you say something about the project?
Now we are discussing about we are like based on the license implementation system, and then we are planning to extend it.
Yeah, but if you are working, for example, in other projects, you can just propose. I mean, it's not very important to work in the same license base. So if you are working in another project, you can just take this project as a project for the course, and you can. So we just need any project where you are using deep learning, machine learning, as a project. Could be your project. Okay. Okay. So thank you very much for today. I mean, now it's at 12. I mean, the plan today was to finish early and try to make also a few slides. I don't know, should we use some few slides in the last 15 minutes? Okay. I can try to.
No, I just saw the link.
I mean, last time it was lecture number 8, I guess. 8. Do you remember which slides? Oh, sorry. No. I don't want. Is it okay? Can you see my screen online? So last time we talked about, we took some examples. It was nice examples for text because it's important to work with text as well. So we have been talking about, okay, so those intermediate outputs, if you want to plot the output from one layer, it should be possible to use it to do this. So last time, for example, we just, just very simple examples. For example, we have here sequential API. We use this sequential API to build a model for endless data set. So we use here some dense layers, It's not CNN. So it's just some dense layers. And if you want to plot the output from one of those layers, it should be possible to do it. So we can extract, we can build a new model. So for example, here, if I want to plot the output from in layer, it should be. So for example, I want to plot the output of the hidden layer. So you can just create a new model using the model API, and I can, the input will go, the input to the model will be the same, but I will get the output from this specific hidden layer. So you can give it a title, you can give it a name, for example, or you can just use numbers. As who did it today? I guess Muhammad used -6. So you can get the output from those and reconstruct it and just the plotting. So when the input is 7, this one will be the output from this hidden layer, and this one will be the output. So it's something nice to just understand what will be the output from each hidden layer. Data representations for neural network. This part, it's we will do it by time. We split our data, for example, and it's just what will be the size of my input, for example. So it will be number of features, the number of time steps, number of samples. So one time is important when we are working with the time series. Maybe time itself is not important, but the order is important, right? So if you have a time series, for example, so we have day 1, day 2, day 3, 4, 5, 6, and so on. We have the date. Maybe the date itself is not important, but the order of the data point, this is the most important. So just remember, when time is important, don't shuffle your data, and when you are splitting it, just increase the order. So maybe the first 50% will be used for training, and the last 20% will be used for testing. Don't shuffle your data sets when order is important. Order is important in time series. For example, we have stock price, for example, we need to predict the stock price next week. So in this case, we cannot mix it, because if we mix it, we will destroy it. Because we have some trends, we have seasonal impact in the time series. So be careful about this. So for example, the data set of stock price, every minute we store current price, highest and lowest price in the past minute. So in this case, we will have 3 values. We have the current price, the highest and lowest in the last minute. So each minute is encoded as a 3D vector, for example. An entire date of trading will be, if people are working 6.5 hours, right? So it will be 6.5 times 60 minutes, because we are recording each minute, right? So it will be 6.5 times 60, so it will be 390 values. Yes.
Just didn't get, what do you mean by we have to store it as a 3D tensor?
It's just like an array or a matrix, right? So so for example, if we are recording 3 values in one day, in one working day, so we will have 390 values times 3. So 390 value, 90 examples or samples, and we have 3 values, x1, x2, x3, for example.
Like
So,
3D.
yes, so it will be like this one, right? What does it mean by 3D tensor? If we have in the whole year, in the entire year, we have 250 days, working days, right? Because it's 5 times, maybe 5 times 4 times 12, for example. So if we have 250 days, so in this case, we can store it in a 3D tensor, like days, minutes, correct? Values. So it will be like this. So, and of course, I mean, this one, we will keep it in this order, because this is the order where data were collected. So if you want to get day 1, so it will be just 1, and the rest will be the same. So for day 1, day 2, 3, 4, 5, 6, and so on. So it will be easy to manage your data. So the data sets of tweets, another example, data sets of tweets where each tweet is sequence of 280 characters out of an alphabet. I mean, the alphabet in general is 128 unique characters, because we're using the dots, using the colon, using, so it's in total it's 128 unique characters in the keyboard. And from those, we have 280 each tweet size, maximum size. From this. So we need to encode it. How can we encode it, for example? So we have the digits, it's from 0 to 9, lowercase letters, it's from A to Z small, uppercase from E capital to Z capital, bank tuition, so in total it's 128 in total. So each, if you can just imagine, it will be one hot encoded, if we need to encoding it. So if you have, for example, my name is Ibrahim, so I will be, I will be 1 when it's a small I or a capital I, for example, and the rest will be zeros. So each digit, each character will be represented as a vector of 128 values. It will be binary, it will be zeros everywhere except when it's my letter, for example, R. So in this case, in this setting, each character can be encoded as a binary vector of size 128. All zeros except where the index corresponds to the character, like one hot encoding. So each tweet can then be encoded as 2D tensor of 220 times 128, right? So now it's, but almost it will be zeros everywhere except at the index of each respective character. If you have a data set which consists of 1 million tweets, how can we encode it, right? So it will be a 3D tensor as well. It will be 1 million times 280 times 128. So this is how we will put it in. So it will be 3D tensor. So making it will be much easier, right? And of course now you can imagine how much memory we need. So it will be this number of digits or this number of values. If each value will be, we will store it as a 32 bits, for example, 2 bytes, right? So in this case, we can calculate, we can imagine how much memory we need. And you can decide how much GPU memory I need for training your model. if you go for mini batch gradient, for example, so we can decide how much memory we have, how we will design, how we will process our memory. So this is very important to understand how much memory you have or how much memory you need. So this is another example. If it's image usually it's RGB, for example, in 3 dimension. So it's and the color depth, for example. So the grayscale image has only 1 dimensional color. If it is RGB, it will be 3 values. So we have height, width, and RGB, correct? If it's a grayscale, so like in this data set, we have height and width only, and it's a grayscale, so it's one channel. So a batch of 128 grayscale images of 28 times 28, it would be 128. So it will be 128 times 22 times 22 times 1. So it will be 4D tensor, correct? Because it's one channel. If it's 3 channels, it will be 328 times 28, 28. So this is how we will deal with those images. So video data, in fact, it will be the same like images, but we need the frames per second, how many frames per second, right? Because so it will be samples, okay, it will be samples times the frames, times height, width, color, depth, right? So this one, it will be 3, for example, because it's a video, it will be RGB, it will be height, width, and how many frames per second, 20 frames per second, for example, and this is the number of seconds, correct? It could be something like this one. So second 1, 2, 3, 4, 5, 2, and so on. And how many frames? It could be 24, it could be 30, it could be 40. So it will be 5 dimensional. It will be 5 dimensional. So this is an example, 60 seconds. And this is a size, 144 times 256 YouTube videos. This is the height, this is the height, this is the width. And it's 4 samples per second. We will get 4 samples per second. So it will be 4 times 60, it will be 24 frames. A batch of 4 such videos. If we have 4 such videos, it will be 4, 20, 240, 144, 256, 3. So it will be 5 dimensional tensor, for example. So if you want to calculate how much is space in the memory, we can just do it like this one. So in total, if you will store each pixel value in 32 bits, for example, correct? So just multiply all those numbers by the 32 bits. So in total, it will be 425 megabytes. So this is very, very important in designing how the system, how the pipeline look. Because we are building a system, we need to know how much GPU we need, for example, and so on. So this is very, very important information for us. Because Ricardo is outside, what time is it now? So, okay, we have 2 minutes. So this one, it's internet video database, right? We mentioned it last time also. It's about reviews. So when you are watching a movie, for example, you just write a review, for example, the review size will be different. Someone, he will write full page, someone will just write 1 sentence or 1 word, for example. So the size is different. So the size is different. We have here 50K movies, reviews for natural language processing, for text analytics, for it's a sentiment analysis. We need just to say it's positive, negative, good, bad movie, right? So it's a very simple. So each review is a sequence of words of different length converted into a sequence of integers. We know we have 128 integers, so it's easy to encode it into, correct? It's easy to encode it into a vector. So each integer stands for a specific word in a we will build a dictionary. So we will select the top 10,000 most popular words. We have the code in use in my computer. So we can just from this one we can find unique words. We can tokenize it, and we can get most popular 10,000 words. We are just selecting the most common, most popular 10,000 words, for example. So we have 50,000 reviews. We divided it into 25,000 for training, 25,000 for testing. Some of them 50% positive reviews, 50% negative reviews, and each review will be a sequence of words. But the size will be different. We will omit all words except the 10,000 most popular, right? So maybe if you are writing a review, maybe it will end up by 10 words, maybe 20. 200, because we will omit all other words. We will just select the most popular words. we will keep those. The rest we will ignore. So when you read it, after that it will be something that does not have any meaning, but we keep the most popular words. Each review sequence of words will be converted into a vector of 10,000 dimensional vector of zeros, except word index, because we need to encode it. So if I have a dictionary of 10,000, correct? So each review will be coded into those a vector of 10,000 values, right? It will be 1 at the index of the words. Otherwise, it will be zeros. So maybe your review will be 100. So in this case, will be 100 once, and the rest will be zeros. So now we are converting each one into a fixed. This is the problem of machine learning. We are working with a fixed size of inputs, correct? But when we are working with RNN, for example, we don't have this problem. We can work with the sequence. But when we are working with convolutional neural network or just feed-forward neural network, we know that the input size must be fixed. So when we convert each review into this vector, which has a size of 10,000, we are sure that we have a fixed length. It will be 10,000, just 10,000. You can do some word embedding later on. Word embedding means it's a light code encoder. So we will just try to squash it into a vector of float values, which is much less, much smaller, maybe 64 or 128, for example. So I can convert this 10,000 into like a bottleneck line into a subset of features, which is more, it's representative, but also it has, it's much less, because the problem, if I reuse this 10,000, if your review is 100, so we'll have 101, and the rest will be zeros. So it does not make any sense.
Maybe 2, for example, a word comes 2 or 3 times. A word comes 2 or 3 times.
We will use it only one time. This is a problem also. So this is a problem here. So if you will use a dictionary of unique 10,000 words, and you are just using repeated something, it will not be considered new, right?
We should add the index, for example, a word A. Or like
How many times? You can count it. You can just write, yeah, of course, it could be.
Instead of 1, for example, THEB word comes 3 times.
Yes, so instead of using one binary digit, 1, it could be 3, for example, 4. Yeah, but yeah, it could be possible, yes. But we need to normalize it at the end, so we will have float values. Yes, it could be possible. So Hamad mentioned that if you have something repeated, for example, so I'm just writing this review is beautiful, it's very, very beautiful, so very, 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 so I use this 3 times, which means it's really very possible. So it could be, so if very is one of those words in that dictionary, so in this case, we can just mention that as we mentioned 3 times instead of only 1 time. So it could be 1 time if you insist to be binary, we will just use 1. If you want to count number of repeated words, so it will be 3 for example. So this word, the size of this vector, it will be 10,000 values, correct? So 10,000 is too much. It will have lots of zeros in fact, because not all people are using the same set of vocabularies. So in this case, we can just reduce it using word embedding. Word embedding is a neural network where this one will be the input, and we try to reduce the size of the like encoder. So we try to reduce it as a set of subset of features, and just it will be float values, right? So we can use word embedding. So at the end, the data set will be represented as a 2D tensor. So the size will be, the first dimension will be 50,000 because we have 50,000 reviews, and each review will be represented by a vector of size 10,000. I guess Ricardo is outside, so we can just finish here, and next time we will continue with this again. And yes, so thank you very much for today, and please work hard, and we will meet again next Monday. Thank you very much. Please, if anyone has any questions, just send me an email during the week, and we will meet again next week. And please, Muhammad, just remember to send me the code which you did today. So, and also it's you and Hamad and Bjornar. This your code for. I need to make something for this model. It's called YOLO, and also VGG16 and stuff like this. I want to. Okay. So we need to use it for just some examples for predicting this minimum bounding box. Yeah. And the most important is the data set. If it's something easy, so. Okay, so thank you very much for today.